In this lesson, we're going to look at limits as x approaches a constant. So this next problem requires an understanding of one-sided limits. Consider this function f of x equals, we have this big, massive, ugly piecewise function. We have, looks like 5 pieces. All right, so we want to consider the function 1 over x squared as long as x is less than negative 1. We say that f of x or y equals 2, so the y values are all 2 on the x interval, including negative 1 up to 1. Then we have y equals 3 if x equals 1. That right there should cause you pause. Since x is actually equal to one value and y is equal to one value, okay, that suggests that we have the ordered pair 1, 3. X is 1, y is 3, or f of x if you want. The fourth piece is linear, x plus 1, only on the restricted x values when x falls between 1 and 2, inclusive of 2. And then the y is equal to negative 1 over quantity x minus 2 squared on the x interval greater than 2. All right, so we want to, in part 1, we want to sketch the graph of f. So let me help you get started. We'll do 1 or 2 problems and then I'll leave you to do the rest of them. All right, when you're going to graph this piecewise function on a coordinate plane, it's good to kind of look at, first of all, the restricted x values for each of the corresponding functions or pieces or equations. So I'm just kind of eyeballing all these x values where breaks occur or points occur. So it says if x is less than negative 1, so I'm going to put negative 1 here. I have a break at x equals negative 1. Then I have a break at positive 1. So I'll put that about right here. I have a point at x equals 1. And then I also look that I have the linear function x plus 1 between x equals 1 and x equals 2. And this last function I'm going to graph is going to be graphed where x is greater than 2. All right, so we've got a bunch of different functions, some linear, some constant, some of these togetherness pieces right here, and it's all going to be kind of combined and make this real interesting graph. And just for the sake of putting another x value here, I'll put negative 2. All right, so we're going to graph piecewise functions by hand. Yes, you'll have to do a few of these, so it's probably good to go back and review graphing piecewise functions. All right, you could create a T-chart for each of these pieces and plot a bunch of points depending upon the restricted x values. I'm going to try and graph this piecewise function based on my understanding of parent functions. So let's think about the graph 1 over x squared. Just real quickly, 1 over x squared is this function right here. Now, I would want this entire graph if my x values weren't restricted. However, they are. My x values on this graph are restricted to only include x values less than negative 1. So basically, you don't want any part of the 1 over x squared graph that's to the right of x equals negative 1. So what I do instead of doing a T-chart is I think about, okay, well, let me let x be equal to negative 1, plug in negative 1 to the equation, and when I evaluate that, I get 1 over 1 or just 1. So f evaluated at negative 1 will give me 1. So at negative 1, I'm going to go up to positive 1. Now up here, I'm going to put an open circle because I don't include x equals negative 1. And so then I'm going to kind of eyeball this graph and go, you know what? This is the part of the graph I want where x values are less than negative 1. So all I want is this part of the branch right here. And make sure and draw it so it suggests that it's getting closer to a horizontal asymptote of y equals 0. So all we did was we grabbed this piece right here based on the restricted x values. All right, let's look at the second piece. I want to graph y equals 2, a horizontal line at y equals 2, only when x is negative 1 up to x values of 1. So I'm going to go over to x equals negative 1, and I'm going to go up to 2. And I'm actually going to put a point here. I'm going to fill that circle in, which is fine because I'm lined up vertically above an open circle. So then I look at the other end point of the restricted x values and I go, okay, x equals 1 gives me an output of 2. So I'm going to come up here, but I'm going to put an open circle because x is less than 1, not or equal to it. So here's my horizontal piece of y equals 2 on this restricted x interval. We already said that the third piece is a point. So x equals 1, and I need to go up to 3, and I'm going to put a point here. That's a result of this middle piece. So, and this is okay, we still have a function. We have one open and one closed circle, that's fine. Let's move on to the fourth piece. Now, think about what x plus 1 looks like. It's just a linear function. I'm going to draw the entire graph. It has a y-intercept of 1, and the slope is 1. So that linear piece would look like this right here. But do I want this entire line? No, I only want this part of the graph where x values fall between 1 and 2. So just kind of eyeballing it, I'd say, well, maybe that's 1 and that's 2. So all I want is this part of the graph right in here. So how do I use parent function graphing to kind of help me, to sketch this piecewise graph? Well, I mean, I kind of looked at the line being transformed, but how do I put all that over here correctly? So I'm going to go to the x value at the left endpoint of 1. I'm going to input 1 for x into the equation. So when x is 1, y is 2. But I don't want to fill that circle in because it's not x is not including 1. So I actually am going to start that linear piece here. Now let's go to the other end of the restricted x value to 2. Now plug in 2, add 1, so the output is 3. So at 2, 3, I'm going to have a filled in circle for inclusion. And so between x equals 1 and x equals 2, this is the part of the linear function that I want on my piecewise graph. All right, for the last piece, then as x values are greater than 2, I want to draw that part of this graph right here. Well, based on our parent function, 1 over x squared that we saw up here, I can see I'm going to shift that togetherness graph right to, and I'm also going to reflect it because of the negative. So let's see if we can kind of draw a graph of that. Right to. So now the asymptote that used to be on the vertical axis, the y-axis, has been shifted right to, and I have togetherness, but it's got to come downward like this because of the negative that transforms the graph. So do I want to put all of this graph over here? No, because then I wouldn't have a function. I only want this part of the graph where x values are greater than 2. Well, here's 2. Cover up everything that's less than 2, and all we're going to draw then is this graph right here, this part of the graph. So what I might do is kind of lightly draw in a vertical asymptote, and then I'm going to have the graph look something like this. Make sure and extend the x-axis so that the graph suggests that you're approaching but never touching that x-axis. And then carefully draw down here to suggest that you're approaching the vertical asymptote down here in the negative direction. All right, so just hopefully that's a good reminder of how you guys put together piecewise functions. Like I said, you might have used a t-chart, and if you're comfortable with that, look back at those notes and remind yourself. But these functions themselves were pretty basic that we have an understanding of, so we could just kind of use some point plotting to help us put this graph together. I know that this is kind of an interesting place right here where you have a vertical asymptote, but it's only applied, that vertical asymptote only applies to the graph that's to the right. And not to the left. I know that's kind of strange, but we see strange situations and we have to be prepared to deal with them. Okay, now let's go ahead and answer a few of these questions. So question A, what's the limit? Now, let me back up. The title of this worksheet is Limits as X Approaches a Constant, which means X is approaching this constant number, X is approaching that number, X is approaching that number. All of these C values, if you will, are constants, meaning I'm not considering as x goes to positive or negative infinity. That's a later lesson. Okay, so right now, limits as x approach constant. All right, so what's the limit as x approaches -1 from the right? Well, if I'm approaching -1, I'm just drawing a little number line from the right, okay, then I'm at numbers that are bigger than -1, because numbers to the right of -1 are bigger than -1. So I can go to my graph, I can locate -1. Okay, now remember, a limit isn't a functional value question. I'm approaching -1 from the right. So let's get on that part of the graph that's to the right of x values of -1, and we're going to start moving that way. So what's the intended height as I approach -1 from the right side? I never want to be at x equals -1. I just want to approach it. and the intended height is read from the vertical axis. Yeah, vertical axis. So the y-axis. So that limit is 2. So the right-hand limit exists, and it's equal to 2. All right, this one right here is x approaches -1 from the left. Well, here's -1. Let's get to the left of it, and let's make sure we're going to start moving back this way. But get on the graph, and we're going to have to start traveling upward. Well, this open circle with no part of the graph on the other side of it suggests that my intended height as I approach -1 from the left is going to be 1. So individual one-sided limits can exist, but now when we look down here at question C, it says, so what is the limit as x approaches -1? Well, we have to consider the behavior from the left and the right, and because we have different values, we would say that this limit does not exist. Let's come over here. Anytime you have a D&E, let's come over here and justify. And it's as simple as not saying, don't say 2 doesn't equal 1. We all know that. But in calculus, what's the notation? Well, this doesn't tell anybody you considered limits, but this notation does. And we're talking about the F graph does not equal the right limit. So let's make sure and practice that justification. All right, and then it continues, and you just look at different constants as x approaches different constants, and then you report the answer. Okay, I'm going to jump all the way down to K. K says on the same f of x graph, it tells us what graph we're looking at, as x approaches 5. Well, 5's over here. As x approaches 5, okay, well, what are the y values getting closer to? Well, it looks like they might be going to 0, but how can we be sure, you know, that that intended height is going to be 0 there? Let me kind of extend this a little bit, and let's put 5 on here. So that's 1, 2. I'd run out of room, but let me say that this is 5 right here. What's the limit as the x values approaches 5? Now, notice it doesn't say from the left or the right, but it's our responsibility to look at the limit from both the left and right hand side. So let me just think about if I'm at 5, but to the left of it, it looks like the intended height is going to be right here at this point. If I approach 5 from the right, it looks like the intended height is still going into that same point right there. And it would be this way because this part of the graph is continuous here, just this little piece is. So usually when they don't have from the left and right, probably nothing interesting is happening on the graph. It's probably connected there. So do I want to put 0? No, I don't, because this is the intended height right here, which is probably a y value close to 0, but not 0. How can I find the exact limit answer? Do I have an equation for this part of the graph that I could maybe plug 5 into and then find the actual y value? Because the y value at x equals 5 is the intended height from both sides. I sure do. So now that we don't just have a graph, but we also have equations, we can use those too to assist us if we get stuck. Okay, so what piece am I talking about? Well, x is approaching 5, and 5 is a number that's bigger than 2. So I would insert 5 into this equation for x. And when you do that, that's called a direct substitution. That's going to be some of our later work. I would plug in 5 for x, square this, I'm going to get -1 over 9. Which makes sense when you think about it, because -1/9 is a very small number and it's close to 0. So the point is this: you have equations that represent these pieces. If you can't evaluate the limit from the graph, go back to the pieces. For example, look at A. A says, we know the answer is 2. A says, let's approach -1 from the right. And without even looking at this graph, I didn't even need to have this graph actually to answer all these questions. If I approach -1 from the right, the numbers that are to the right of -1 are bigger, greater than -1. So I'm going up here going, well, what piece should I plug -1 in if I'm at x values close to -1 but bigger? Well, this is less than -1 to the left. Right here in this inequality statement, this says x is greater than or equal to -1. So these are x values that are bigger than -1. So in that case, I would substitute in my -1 x value to the x that's in this equation. Well, there is no x, so my answer is 2, and we ended up with 2. Let's look at B. Could we have found 1 without looking at a graph? Absolutely. The limit as x approaches -1 from the left. So here's -1 again. I'm going to approach -1 from the left. That means my x values are smaller or less than -1. So let's find the restriction that describes x less than -1. That would be your top piece. So now on the top piece, once we've identified x values less than -1, then I can plug in that x value of -1, work it out, and I am going to get 1. So graphically or numerically, analytically, I guess, okay, if you have the equations and the graph, I would just double check myself. So hopefully that'll help you with the rest of it. And if I were you, I'd use both my graph, but then I would try and confirm it with the equations as well. All right, so complete the rest of these problems. All right, if you need to take a brain break, go ahead and do so. But what I'm going to do is I think we all should work on this last question right here. And I'm going to work on this question on the back of this worksheet. Okay, you can do this on your own notebook paper too as well. So take a moment and read through the problem that you're asked to solve down here at the bottom. All right, so we want to know what are A and B in both these equations, the top and the bottom, so that my limit exists. So for my limit to exist, the left limit has to equal the right limit. And we're talking about x approaches 2. So in that case, I'm really going to want to focus on this is the right limit because x is greater than 2. And this is going to be the left limit because these are x values less than 2, to the left of 2. I want these two answers to be the same. I want the left limit to equal the right limit. And I want to do that, and I want to find what A and B are to make that true. We also additionally know that the left limit and the right limit should be equal to the functional value when x is exactly 2. Well, when x is exactly 2, we know the y value, the functional value, is 3. So you could do a lot of mental work here, okay, but I think we might want to start working on a mathematical process in which we can answer this question. It's a very popular AP question. So let me turn the paper over. And I'm going to go ahead and quickly rewrite the piecewise function on the back so I don't have to keep flipping back and forth. All right, so I have this linear function for x values greater than 2. Then I have a point at 2, 3. The ordered pair x is 2, y is 3. And then to the left of x equals 2, I've got a quadratic, and it looks like that quadratic's going to open down. You know, think about the math background that we have that we bring to this course, right? We have a linear function and a quadratic function. So if you were to draw this graph, it would be a quadratic, because x is less than 2, we'd have a point, and then after x is greater than 2, to the right of 2, you would have a linear piece. So the break occurs at 2. And I do know that 2, 3 is an ordered pair that's on this function. So to the left, they kind of have these out of order. We have a quadratic piece that opens down for values less than x equals 2. So maybe the graph comes off like this, or maybe you can go something like this, not sure. And then to the right of x equals 2, we have a linear function. So maybe it does something like that. But what we want is we want the left limit to equal the right limit. We don't want to jump discontinuity. And we want those limits to go into the same point that's there. So basically it's saying we really want our graph to be quadratic here and then linear here. I mean, it very well could be linear with the negative slope depending upon the A and B values. All right, how do we do that? Well, what have we learned so far? Well, we've learned that the limit as x approaches 2, and I'm going to do the left, smaller values, or to the left of 2, so less than, of this function, b minus ax squared. Instead of putting the generic f of x, I'm going to actually put the corresponding piece to the side of the limit I'm approaching. That has to equal the right-hand limit as x approaches 2 from the right. So numbers bigger than 2 would be suggested by this restriction, and then instead of putting f of x, we're going to put this quantity here. Sometimes you'll see parentheses around all this. It's probably a good idea. And not only do we want the left and the right limit to be equal, we want them to equal the functional value f of 2. So let's see what we can do here. Well, I've got a statement with 2 equals. So I know that f of 2 is equal to 3. So now I want the left limit to equal 3, and I want the right limit to equal 3. A lot of ways you can solve this mathematically, but I think what I'll do now is I'm going to actually plug in 2 for this x. That's a direct substitution. We can do that because we want to kind of know what the y value would be on this function when x is 2. So b minus a, and then 2 for x, and then square it. That expression has to equal the direct sub in here on this linear piece. When we plug in 2, what's the y value we want on this line? Well, a plus b times 2, or 2b. So the equivalency of all of this suggests that, well, maybe I could separate it and say, okay, well, let me take this first piece. B minus, that's 4a, has to equal the 3, and a plus 2b has to equal 3. Well, I guess thinking back to Algebra 2, there's different ways to solve this. You could do substitution method, or you can do the linear combination, also known as the elimination method. It really just depends upon what you want to do. I see that it would be easy to take this equation and add 4a to the other side and get b by itself. So b equals 3 plus 4a. I'm going to do the substitution method to where now I'm going to plug in 3 plus 4a for that b. So a plus 2 times 3 plus 4a equals 3. Now we have an equation with just a in it. So let's do the necessary solving. A plus, distribute, 6 plus 8a equals 3. All right, let's collect my a's. I've got 9a plus 6 equals 3. Let me subtract 6. So 9a equals negative 3. Divide by 9. Clean this up. A equals negative 1/3. Well, I've got A. Now how do I find B? Taking you back to Algebra 2 and the substitution method. Well, let's come back over here to this other equation and let's insert negative 1/3. So now, I'm coming back up here. Let's find B. It's 3 plus 4 times negative 1/3. So B equals 3. This product right here, that's a fraction, is minus 4/3. Let's get a common denominator. So let's make 3 have a fraction or denominator of 3. So that makes that 9 over 3. 9/3 is 3 minus 4/3. So B equals 5/3. Oh, sorry about that. So the answer is going to be the ordered pair, negative 1. Well, I guess we're not doing an ordered pair. We're just finding values of A and B. So at this point, I would just box these and say these are my answers. Whew, that's a lot. But remember, they want the left limit to equal the right limit, but then both those to equal the functional value. They want that graph to come into the same point there. So these are the A and B values that when we're placed back in for these A and B values would create a graph so that it's connected and it's continuous. And that was the purpose. Just real quick, since I have another minute, I wanted to remind you about the elimination method. Let's go back and let's say you didn't want to do the substitution method here. So say I have these two equations. Here's another way. This will come up. I wouldn't waste my breath or your time if it's not coming up again. Or A plus, or this is and, sorry. So we're done here. That was the substitution method. Let's talk about the elimination method. For the elimination method, we stack them on top of each other, the equations. Okay, so, and we line them up so that all the terms match up. We have like terms. So I'm going to have to rearrange this equation a bit. So I've got equals 3 here, but I'm going to put negative 4a first and plus b here. The elimination method had us stack them up, line them up all the terms, and then we could eliminate either the A's or the B's. I think it was X's or Y's before. So in order for me to eliminate the A terms, so all I have are B's, I'm going to multiply the top equation by 4. If I multiply this A by 4, when I add down, those will cancel. So I'm going to show that I'm going to multiply 4 in here. So actually, I'm going to draw a little squiggle here to indicate I'm not ready to add down yet. So distributing 4 in and recording it, rewriting the bottom equation. Now I'm able to add down, and one of the terms, the A term, will cancel, and I'm left with 9B equals 15. Divide by 9, divide by 9, divide out, B equals, 3 is a common factor, we're going to end up with 5/3. Now in order for us to get A, we would go back to one of the two original equations and insert this fraction for B, and then continue the solving like we did over here. So hopefully that's a quick review of something you learned way back when, substitution, and also the elimination method. And it assisted us in finding the answer to this limit question.